So in this section, we'll be looking at atomic structure. So it's section 3.3 in our book. So the structure of the atom. In 1897, a man named J.J. Thomson did an experiment that showed that atoms contain electrons, and he used something called a cathode ray tube. So what he did is he had two plates. One was negatively charged, one was positively charged, and this was just a voltage source. You can think of it like a battery, and a battery has two sides, a positive and a negative. He had some gas in this glass tube, and he was able to see that he had this stream of negatively charged particles. And this charged particle was called a cathode ray. They didn't know what they were, but that was the term that they used, a cathode ray. Now, if you have a TV set, not a flat screen, but a more traditional TV set, you have a cathode ray tube. It sends a stream of electrons to your screen that excites whatever coating is on the screen so that you can see your picture. So the cathode ray has a positive and a negative, and they can deflect these electrons and make it bend. So if electrons are negatively charged, this has to be a positive so that the electrons bend towards it. So I'm going to turn on this video so we can watch it. And
The ray tube is the forerunner of the television tube. It is a glass tube from which most of the air has been evacuated. When the two metal plates are connected to a high voltage source, the negatively charged plate, called the cathode, emits an invisible ray. The cathode ray is drawn to the positively charged plate, called the anode, where it passes through a hole and continues traveling to the other end of the tube. When the ray strikes the specially coated surface, the cathode ray produces a strong fluorescence, or bright light. When an electric field is applied across the cathode ray tube, the cathode ray is attracted by the plate bearing positive charges. Therefore, a cathode ray must consist of negatively charged particles. We know these negatively charged particles as electrons. A moving charged body behaves like a tiny magnet, and it can interact with an external magnetic field. The electrons are deflected by the magnetic field. As expected, when the direction of the external magnetic field is reversed, the beam of electrons is deflected in the opposite direction. In 1897, J.J. Thomson, an English physicist, determined the charge-to-mass ratio of an electron. He adjusted the electric field so that the electrostatic deflection, theta E, was the same as the magnetic deflection, theta B, and was able to calculate the charge-to-mass ratio of an electron using the following equation, where E is the applied electric field, theta is the angle of deflection, B is the applied magnetic field, and L is the distance traveled by the cathode rays. Thomson determined the charge-to-mass ratio of an electron to be negative 1.76 times 10 to the 8th coulombs per gram.
so that last part was pretty advanced, but I thought I'd keep it in there so you could see what the possibilities are for your future. So again, it's just a traditional TV set is a cathode ray. So it was J.J. Thomson who determined that every substance has electrons. He came up with the plum pudding model of the atom. So this is the history of the atom before now, obviously. So the spherical cloud of positive charge, they didn't know about the nucleus yet. He thought the electrons were embedded in like a pudding. And a pudding is just like your chocolate pudding that you might have, or maybe if you think of Jell-O with something in it. A man named Rutherford followed him, and he used something called the gold-foiled experiment. He had a lead shield around the source of alpha particles, and alpha particles are helium nuclei. So they're stripped of their electrons, so they're positively charged, and you have this beam of alpha particles going through, and what was amazing about him, what he expected with the plum pudding model, which is what he was working under, he expected all of these to go straight through, maybe with a little bit of a deflection. What was his genius is that he noticed these very, very few that shot backwards. Because of the results of this experiment in 1911, he was able to determine that the positive charge isn't like the pudding, but it's actually concentrated in the center. And Ernest Rutherford was responsible for the nucleus. He determined that atoms have a nucleus in the center. Now, he didn't know really what was happening with the electrons, but Rutherford did a whole bunch of studies with alpha particles, and he came up with beta particles, which is another form of radioactivity. So the structure of the atom, due to Rutherford's experiment, changed from this plum pudding model to Rutherford's nucleus-centered model. All right, so Rutherford discovered the nucleus of the atom using his gold foil experiment. Really important discovery for us. There's the nucleus, very, very tiny. He knew that it had a positive charge. And we now know that that's due to the protons. Rutherford was so surprised, he said it was like howitzer shells bouncing off of tissue paper. So that's like a cannonball, say, being bounced back at you if it hit a piece of paper. He just didn't expect that to happen. So he concluded that the nucleus contains protons and neutrons and most of the mass of the atom. Now, I need to correct myself. He didn't know anything about neutrons. They weren't discovered until 1932. But he knew that protons were there, and he knew that most of the mass of the atom was in the nucleus. We know that electrons have a -1 charge, and they're located in the electron cloud. Their mass compared to a proton or a neutron is just 1/1836. They're so small, we tend to ignore their mass. A proton has a +1 charge. We say its mass is 1, and it's located in the nucleus. The neutron has no charge. It has the same mass as a proton, and it too is in the nucleus. So now we're to our model of the atom. Now, atomic number, which can be represented by Z of an element, is the number of protons in the nucleus of each atom of the element. So if you have carbon and it has 6 protons, its atomic number is 6. Phosphorus has 15 protons, its atomic number is 15. Gold has 79 protons, its atomic number is 79. Isotopes. You've been working with isotopes for the last few days. Isotopes are atoms with the same number of protons, but different numbers of neutrons. They have the same chemical properties, but they have different physical properties. This is hydrogen, and hydrogen can have 1 proton, so its mass number is 1. Hydrogen here has 1 proton and 1 neutron, so its mass number is 2. This hydrogen has 1 proton and 2 neutrons, so its mass number is 3. So remember, these orange ones are neutrons. These guys are protons. Remember, the proton tells you the element, so if Z equals 1, we know we're dealing with hydrogen. So I wrote the nuclear symbol. You could also write the hyphen notation. Your second one is H2, that's called deuterium, and your third one is H3, which is called tritium, and that is a man-made isotope. Mass number. Mass is the sum of the protons plus the neutrons, so you could just write an equation. Mass number equals number of protons plus neutrons. You could abbreviate this with this bottom equation. Remember, A is your mass number. So our nuclear notation is like this. You've been using this with your isotope activity. Z is your atomic number. A is your mass number. And X is your chemical symbol. And you get that from the periodic table once you know the atomic number. A nuclide. A nuclide just refers to a particular isotopes. So, for example, if I used carbon 13, let's write it properly, atomic number 6, mass number 13, this is a nuclide of carbon. It's a vocabulary word. Nuclides of hydrogen. Hydrogen has special names: protium, deuterium, and tritium. For the notation, this is hydrogen 1, deuterium is hydrogen 2, tritium is hydrogen 3. Tritium has 1 proton, 2 neutrons. Deuterium has 1 proton, 1 neutron, and hydrogen has 1 proton, 1 neutron. Hyphen notation. You take the name of the element and the mass number. You can also just use the elemental symbol or chemical symbol and the mass number. So this isotope of helium would have 2 protons because it's helium, and remember the mass number, you subtract the number of protons and you get 2 neutrons. So if I asked you how many neutrons, you have to do a little bit of subtraction to calculate it when you look at the hyphen notation. When you have an ion, protons minus electrons give you the charge on the ion. So let's look at the lithium ion. It has 3 protons, 4 neutrons, 2 electrons. So its nuclear symbol would be 3 for 3 protons. The mass number is 7, so that's your A for mass number, and there's your nuclear symbol. If I asked for hyphen notation, you could write Li-7. You could also write lithium-7. For the charge on the ion, you need to look at the protons and the electrons. Take your protons minus your electrons, and that will give you your charge on the ion. So we have 3 protons minus 2 electrons, we get a +1 charge, and we would write that Li 1 plus. And this would be the ion. Let's look at chlorine. If we looked at nuclear notation, 17 protons, add together your protons and your neutrons. 35 is the mass number, so that goes up top. If I asked for hyphen notation, 35, I could also write the name chlorine -35. Let's figure out the charge on the ion. Take your protons, 17, minus 19 electrons, and we get a -2 charge. So you'd have Cl 2 minus. You do change where that minus sign is. And this would be the ion. Remember, this is called the nuclear symbol. This is called hyphen notation. So, when we go back downstairs, you'll finish your isotope activity.